Hello, my name is Erin Bugby. This is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. The title of this talk is Cognitive Models of Sequential Choice in the Optimal Stopping Task. I would like to start by acknowledging my team of co-authors at Carnegie Mellon University and the Air Force Research Laboratory. The optimal stopping problem is a sequential decision-making problem involving choosing when to take an action to maximize expected reward. There are many different tasks that involve the optimal stopping problem. One example of this is known most commonly as the secretary problem, in which the goal is to hire the best applicant for a position, and a decision about each applicant must be made immediately after their interview. Once an applicant is rejected, they cannot be hired later. In this work, we focus on the task in which the goal is to select the maximum number in a sequence of numbers independently drawn from a distribution, under the constraint that once an option is passed, it cannot be chosen later. To illustrate the relevance of this problem, consider the task of choosing an apartment. You want to find the apartment that has the highest value to you. If you pass on the apartment, especially in a competitive housing market, there's a risk that someone else will take it and you will no longer be able to choose it. Additionally, you do not want to choose an apartment too early because a better one may appear on the market later. By choosing to pass on an apartment and delay choosing with the hopes of finding a better option, there's a risk that the apartments remaining are of lower value than those you passed. This demonstrates one situation in which these sequential choice problems, and particularly the optimal stopping problem, appear in day-to-day life. The optimal stopping problem is of interest to many disciplines. Optimal stopping theory in mathematics has focused primarily on solving these problems optimally. The optimal strategy has been found to be to choose the first option that is above a threshold that depends on the position in the sequence and the environmental distribution. From the psychological perspective, we are interested in how people perform this type of task and how they deviate from what is deemed theoretically optimal. Much of the previous work on modeling behavior in this task relies on the assumption that people decide using thresholds. One example of this is the bias from optimal model. The bias from optimal model is a Bayesian hierarchical model used to infer the thresholds people use when deciding when to select or pass each alternative in a sequence. BFO characterizes people's thresholds based on how far they are from optimal and how this bias increases or decreases throughout the sequence. The linear threshold model similarly assumes that people make decisions by using thresholds, but in contrast to BFO, this model proposes that people adapt their thresholds linearly over the sequence. In this work, we aim to show that our model can inductively produce choices and risk tendencies resembling those of human participants, without assuming that people use thresholds or relying on optimal thresholds. This brings us to our motivation. Our goal is to build a cognitively plausible model that can inductively produce choices in alignment with those of human decision makers in sequential choice tasks. We do so by developing a cognitive model founded in instance-based learning theory that, in contrast to previous models, is both cognitively plausible and does not rely on the assumption that people use thresholds when solving optimal stopping tasks. We approach this by building a cognitive model that performs the optimal stopping task. Our model is based on instance-based learning theory, which I will discuss in more detail. We then compare the performance of our model agents to the empirical data from Guan et al. 2020. Then we evaluate our model with the bias from optimal model, demonstrating that our model can inductively produce human risk tendencies without the assumption that people use thresholds or needing to rely on optimal thresholds. To validate the predictions of our model, we look at the data from a paper by Guan et al. 2020, in which 56 human participants completed a variation of the optimal stopping task in a between subjects design. For the task, participants were provided with sequences of cats with their corresponding weights, ranging from 0 to 100 pounds. They were instructed to choose the cat in the sequence that weighed the most. They had to either select or pass each cat, and once passed, the cat could not be returned to. If they chose the cat with the maximum weight, they were correct, and otherwise they were incorrect. They were also instructed that the last value in the sequence must be chosen if none were chosen previously. There were 4 conditions. The authors varied the distribution of values, with the values either being sampled from a uniform distribution, called the neutral condition, or a beta 4-2 distribution, called the plentiful condition, since weights are skewed towards higher weights. They also varied the length of the sequence, consisting of either 4 or 8 elements, which in this case were cats. And the participants were told the length of the sequence, but not the distribution. All participants completed the same 40 problems within each condition, with the order being randomized across participants. The order of conditions was also randomized across participants. In this work, we built a cognitive model based on instance-based learning theory from Gonzalez et al. 2003, using Pibble, a Python implementation of IBLT. IBLT leverages some of the cognitive mechanisms of the ACT-R cognitive architecture. Generally, in instance-based learning theory, decisions are made by generalizing across similar past experiences. The learning process occurs by interacting with the environment and receiving feedback. Memory units are called instances, and these instances are accumulated and refined with experience. Instances consist of 3 elements: the situation, the decision, and the utility. In this model, the situational attributes are the value of the current option, which is the weight of the cat for the human subjects, and the distance of the current alternative from the end of the sequence, providing information about how many alternatives are left after the current one. The decision is the choice of whether to select or pass on the current alternative. The utility is 1 if the value of the selected alternative is the maximum and 0 otherwise. Instance-based learning theory relies on 3 main mechanisms: activation of instances, the probability of retrieval of instances, and blending. Instances are activated based on their frequency and recency, the similarity of the instance to past experiences, and noise, introducing stochasticity into the activation value. This value represents how available an instance is in memory, with greater activations corresponding to greater ease of retrieval. Activation also depends on a decay parameter, accounting for the rate of forgetting past events. The activation of an instance is used to calculate the probability of retrieval. This is calculated as the ratio of the activation of the instance to the activation of all instances for the current option. The expected value of an option is calculated using blending. This depends on the probability of retrieval and the outcomes corresponding to the instances for that option. The option with the highest blended value is selected by the decision maker. This IBL model uses the default parameters from ACT-R for noise and decay. With this model, we simulated the choices of 56 agents, seeing the same sequence of stimuli corresponding to each of the 56 human participants. In this way, the model produces choices and performs the optimal stopping task. On this slide, I have provided the technical details of the model. Feel free to pause here and review them before proceeding. For the results, I will present the learning curves of both the human participants and the model agents. I will then present a comparison of the bias from optimal models' inferred thresholds and model parameters for both the human participants and IBL agents. Some of the results and figures here are reproduced and adapted from the materials provided by Guan et al. 2020. Getting into the results, we will first start with looking at the learning curves. The measure is the performance, which corresponds to the proportion of participants who selected the maximum value in the sequence for a problem. The results are blocked by 10 problems, and the lines correspond to the different conditions. On the left, we have the results of the experiment run with human participants. We can see that participants have higher performance on the length 4 conditions relative to the length 8 conditions. We also see that the performance does not increase over time, as demonstrated by the flat learning curves. In other words, participants do not seem to be learning. Further, while there is not much difference between performance by distribution and the length 4 condition, there's a slight difference between performance when the sequence length is 8, with participants performing better in the neutral condition compared to the plentiful condition. On the right are the results of the simulated IBL model agents. Again, the model chooses to select or pass based on the value of the current alternative and the number of alternatives remaining in the sequence, both of which are provided to the human participants. Since the agents have to learn the task while humans were able to read the instructions and understand, there's some initial learning. Generally, the results are similar to those of the human participants, achieving comparable performance. However, we can see that there is a greater difference between the performance across the distributions when compared to humans, with lower performance for the plentiful condition relative to the neutral condition. The IBL model has greater performance for the neutral distribution in both of the sequence lengths. Upon further investigation, we see that the model is erring primarily by selecting options earlier in the sequence than humans. In other words, the model is slightly less patient than participants, but learns to be more patient over time. This explains why the plentiful condition is more difficult for the model initially. The weights for the plentiful distribution are from the beta 4-2 distribution, which is skewed towards higher weights. This means that there are more likely to be high weights that are not the maximum than in the uniform neutral distribution, resulting in errors of choosing values too early in the sequence. Humans understand the trade-off of selecting versus passing on each option from reading the instructions and from their understanding of waiting for something better in sequential choice tasks. While the model agents have to learn this, though they do so quite quickly, and their performance improves to approximately human levels. We additionally compare our model results to the bias from optimal model, introduced in 2015 and applied to this dataset in 2020. As I previously mentioned, the BFO model characterizes the risk propensities of decision makers based on two factors: how far they are from optimal and how this bias increases or decreases throughout the sequence. The threshold is the value above which the current option is selected and below which the option is passed on. The black lines show the optimal decision thresholds, which vary across conditions but are the same on the left and right for both human participants and IBL model agents. Each blue or red line corresponds to a participant's, and since each participant completed all four conditions, each participant's inferred thresholds are represented in each of the four conditions as a line. The left shows the inferred thresholds from the BFO model for the human participants. The right shows the inferred thresholds from the BFO model on the IBL model choice data. Therefore, with this IBL model, we can reproduce these thresholds without providing the model any notion of thresholds in the simulation as the agents make choices. We can see that the IBL model agent thresholds do look similar to those of the human participants. They follow the same pattern and shape and deviate from optimal in similar ways, with some having higher thresholds and some having lower thresholds across the conditions. The BFO model is characterized by two parameters, beta and gamma. Together, these parameters describe a participant's risk propensity in this task. Here we can see the distributions of the parameters. Shown on the x-axis is beta. Beta is how far above or below optimal a participant's threshold is. On the y-axis is gamma. Gamma is how much the bias from optimal increases or decreases as the sequence progresses, or how quickly their threshold declines relative to the optimal line. The IBL model has parameters similar to those of humans. Together, this demonstrates that the IBL model can inductively produce choices in alignment with the risk propensities of human decision makers. It is important to note that the IBL model agent results are not fit to those of the humans. We use the model's default parameters and do not perform any parameter fitting. Therefore, deviations in risk and performance are due partially to the differences in experiences of the agents, as they each see the problems in a random order as the human subjects did. This results in the agents having different experiences to make their decisions from, leading to the emergence of these varying risk tendencies that we see. Overall, our results demonstrate that the IBL model replicates human behavior and generates the BFO model's thresholds without assuming any thresholds. In summary, we built a cognitively plausible IBL model that can generally replicate choices of human participants without assuming that people perform the task by using thresholds and without needing optimal thresholds. We show that the IBL model can be used to inductively produce choices and predict human risk tendencies in the optimal stopping task. It seems promising that this can also be extended to other sequential choice tasks, and we look forward to pursuing this in future work. Thank you for watching this video.